Hi everybody, my name is Jeff Kiel and I'm a Senior Engineering Manager here at NVIDIA. I want to bring you through one of our latest tools called the Nsight Graphics Shader Debugger and give you a feel of how you can utilize it to go after those pesky bugs in your shaders. Now, the Shader Debugger is part of a three-part series of tools that we have available in Nsight Graphics. The first one is our classic Nsight Graphics Capture and Analysis. The Nsight Graphics Capture is really important because this allows you to debug all of your utilization of the API, inspect the state, figure out what resources are bound and what shaders are being used across all the different draw calls and dispatches inside of your frame. We actually have a new feature that's available in 2025.2 that allows you to actually do an offline capture. With this offline capture, you can actually inspect a lot of the state of the frame without actually having to start up either D3D or Vulkan context, which makes it really easy to be able to inspect things on any type of system you want to inspect it on. Next, we also have GPU trace. Inside of GPU trace, this allows you to get a balance of what's happening between the CPU and the GPU, but with a deep dive into the GPU fundamentals so that you can understand the throughputs and how it's utilizing the GPU. You can also use the shader profiler in order to better understand how you're utilizing the SMs or the shader units inside of there, looking for different types of stalls that are hurting your throughput. And then finally, from a debugging perspective, we've got our shader debugger. The shader debugger allows you to actually walk through your shaders just like you do any type of CPU debugger, and you can actually do that both at the source level and at the microcode level. Now, one of the things that's unique about the NVIDIA hardware is that we don't yet support instruction-level preemption for graphics workloads. We do support them for CUDA workloads, and so if you're using some of the CUDA tools, you can do this in a single GPU system. But if you're actually doing it on a graphics workload, you need two GPUs. One that's going to actually be working the desktop and actually going to be running the Nsight host, as well as one that's running your application. You can do that on a single system with two GPUs. Again, one set up to run the host, one set up to run your application. And that can be basically on a system that has two NVIDIA GPUs. Maybe you've got an older NVIDIA GPU lying around that's not currently being used. You can go ahead and use that. But also, if you happen to have an iGPU inside of your CPU, you can utilize that as well, or maybe even another vendor's GPU. Now, you can also do this in two systems, each with a single GPU. And what we'll do is we'll set up a pipe between the two, and via TCP/IP, we can communicate the state so that you can inspect your variables and do all the debugging capabilities you want to. So our example program that we're going to be using is the Vulkan Sponza app, and it's really great because it shows some really neat features in terms of doing a deferred renderer. So this first video is basically going to show you how you go ahead and set up how you're going to do your debugging. So you can see here in the top portion of the dialog there, we've got all the information about your application executable, the working directory, as well as any command line arguments and any environment variables you happen to be using. Then in the lower left, we've got the activity that you actually want to use. And you can use, for instance, the graphics capture, which I mentioned earlier in terms of being able to do a capture that's saved off to file and you can do later inspection, as well as our frame debugger, which is our classic live capture and replay, and you can actually do live inspection of your data, as well as the GPU trace profiler, shader debugger, which we're going to talk about today, as well as the ability to generate a C++ capture and actually utilize Nsight systems in order to do a better idea of how you're utilizing your CPU and GPU resources. So I went ahead and made a video of Vulkan Sponza running with a bug. So this is not initially in the application. I introduced this myself. But you can see here as the lighting is kind of moving around, you'll notice that there on the columns, the light really shines up nicely up to towards the top of the column, but we're not really seeing much interaction on the bottom of the column. And even on the right-hand column, there's not much interaction at all. And then also you'll notice that as the light is moving around, you'll see that instead of having kind of a nice bulbous feature to it, it kind of has this strange line right there through it. And so you can kind of already tell that we've got a bug here in the lighting, and we need to use a shader debugger in order to be able to understand what's causing that. So the first thing you're going to want to do when you come into the shader debugger is look for the shader you want to use. Now, obviously, you have to lose a little bit of understanding and intuition about your application to be able to figure out where you need to debug, although we have some additional tools that you can use to better understand that. But right here, we already know that this is potentially going to be in our SSAO paths. And so we've already kind of done the deferred pass where we've collected all the data for the normals and everything. And now we're actually doing the resolution of that and utilizing SSAO. And so what I've done is I've gone ahead and clicked on one of the fragment shaders, and I'm going to go ahead and add a breakpoint into the source code. So you can visualize the source code as well as any microcode that you happen to have. And you can see I've hit that breakpoint, and it's done a what we call a just-in-time compile of the shader. Now this is important because it allows you to have your application run at full speed, and then just when you want to debug the shader, that's when we will go ahead and do that recompile with full optimizations turned off, and we also will collect all the debug information. But you can see here, I can even step through my shader. I can hit F10 as I would typically would in many different IDEs for debugging, as well as hit F5 so that I can continue on through the shader and again, find out exactly where I want to start my debugging tasks. All right, so naturally, the next thing you want to do once you've kind of honed in basically where you are in terms of your source code, you want to go ahead and open up and figure out what the variables look like at that location. Well, as typical with debuggers, we have a locals window. And as I sit here and as I step through my shader, you'll notice that the locals window is going to be updated. And so as I modify values there, it'll highlight those in red, the ones that have changed. And if I hit F5, obviously many of them have changed because we're in a completely different section of the thread, and therefore we're able to figure out exactly which values have changed during that time frame. So the other thing that you have when you are debugging is the fact that in CPU code, you usually have 5, 10, maybe 15 threads in flight. In GPUs, you're going to have thousands of threads. And so we need some tools to be able to really understand the context of what's happening inside the GPU. And our warp info view is a great way to be able to do that. The first thing we'll show you is you see the columns in red. All of those are basically warps, which are collections of 32 threads that have actually stopped at the current breakpoint that we have set. But then also we have all these green warps. Now the green warps are what we call sympathetic warps. And those are basically warps that are currently running inside the GPU, but they haven't actually stopped at this breakpoint. So they could be at another point of execution in the shader. They also could be executing different shaders in that workload. Now, I don't know about you, but to me, visualizing things in a, in a large, table-like view, especially as a graphics developer, is not really the best way to do that. And so we actually have something that's really specialized for graphics workloads, and that's our focus picker. Inside the focus picker, you can look at all the different warps that you have in flight. So in this case, I've got almost 6,100 threads, and you can look at it as a table. But we also have the ability to actually visualize that along with the current render target. And so you can see here in the upper left, we have a number of different fragments that have already landed in the render target. But then also I see the red and green fragments that are currently in flight, and they correspond to what we saw earlier in the warp info view. And from here, you can even use this to select which thread you're interested in debugging. And this is very important because typically what you'll see is you'll be like, oh, okay, well, like this portion over here, maybe it's near the arm of my character, or maybe it's during an effect or something like that. You'll see a fragment that doesn't quite look right, and rather than kind of trying to remember that's 500 and so many over from the X and maybe 300 and something in Y, instead you just simply like hone in on it, zoom in on it, click on it, and then you can actually debug the individual fragment that you're interested in looking at. So in this bug in particular, one of the things we can do is we can start to see that all of the normal values are all tending to be positive. And if you look at the geometry, you can see that it's kind of facing every different direction, right? You've got walls facing this way, walls facing this way, the floor is from the top and the ceiling. So there's no reason that I can think of logically that all of the normals would face in the same direction, or at least always be positive. And so we can start to see there's probably a bug here with the normals. Now, you're probably also saying, well, we've only hit continue a few times. How is it that I can know for sure that that is the issue? Well, one of the things you can do is you can actually set a conditional on your breakpoint and therefore be able to determine, okay, how often does this actually happen to be positive versus negative? So in this case, what I'm going to do is I'm going to go ahead, I'm noticing that all my values here are positive. And what I'm going to do is I'm going to go ahead and open up the breakpoints window, and I'm actually going to add a conditional. Now, the importance of this is the fact that these conditionals are running in hardware. So this is not something that's like having to be evaluated on the CPU and therefore taking up a bunch of extra time, but instead it's actually being evaluated on hardware, so therefore it's very, very fast. It's going to be very, very performant. So I'll come in here and I'll actually right-click on my condition cell, and I'll basically say condition, so I'll be able to edit that condition. And I'm going to type in normal and then bracket 0, which is basically the X component of the normal. And I'm going to say less than 0. So the idea here is that I only want this breakpoint to fire when the X component happens to be less than 0. And I hit continue. and I'm going to swap over, and I noticed, okay, my application is still running. So definitely there's never an opportunity or never a time that the X component happens to be less than 0, and therefore it's kind of proving my point here that it does look like my normals are not functioning the way I expect them to. So it turns out that the solution here is the fact that the encoding of the normals is kind of an old school encoding. Normally what you would try and do is you would try and use maybe a floating point value or something like that in order to be able to have both positive and negative values as well as a good amount of dynamic range. But in this case, we actually encoded these as unsigned values. And so typically when you do unsigned values, again, you want to make sure you can have the normals pointing in either direction. So what you do is you do a scale and bias of those values. So you basically scale them down to negative 0.5 to 0.5, and then you bias it to be between 0 and 1 so that everything fits in an unsigned value. And you can see here, that's exactly what I did, or this is an example of how I would typically pull it out when I'm unscaling and unbiasing it. And so this gives me a good feeling of, okay, that was the problem. When I extracted the normal value from the render target, I didn't unscale and unbias it, and therefore everything happened to be pointing in the wrong direction. And so once I make that modification, you can see here that I've got really good lighting on the columns. The fire is interacting as I expect, and I've gotten rid of that kind of strange line that was going there that was causing my lighting to not look correct when the light was moving around on the floor. So that's basically it, what I wanted to share with you about what's going on in the shader debugger. Now, I want to emphasize this is going to feel very similar to you. If you've used Visual Studio Code or any one of the debuggers that are out there that are available, you're going to get a very similar feeling. A lot of the key binding is going to work and everything like that. And so I really encourage you to just dive in and give it a try. Matter of fact, we'd love to hear back from you. We've got the ability inside of Nsight Graphics to, in the upper right-hand corner, is a little kind of a call-out bubble. You can click on that, and then you can give us feedback. That can be a feature request, that could be a bug report, whatever it is that you want to give us feedback on, please let us know. We read all those, I promise, and that will allow us to understand better how you want us to be able to respond to these issues. The other thing I wanted to mention is with the R575 driver, which is basically the next version of the NVIDIA driver, is going to be coming out in early April, we actually made a lot of work together with our compiler team in order to improve the symbolic support for ray tracing workloads. It kind of worked in the past, but we definitely had some issues there, and so we really wanted to improve that so that we could provide better symbolic support. And so now when you actually run your shaders with ray tracing, you'll be able to visualize all of your locals, and you should not run into any issues there. Thanks a lot, and I appreciate your time.